Welcome back. We're in momentum on worksheet 2, problem number 6. A blue rubber ball rolls along a small level surface at 15 meters per second due east. Headed due west is a red rubber ball of the same mass as the blue one, but moving at 22 meters per second. Immediately after the head-on collision, the blue ball is headed west at 21 meters per second. Oh, okay, cool. So we know that the action here is this collision here. Cool. So we're going to draw that. It says determine the final velocity of the red ball, clearly. Is this elastic or inelastic? Oh, that's getting back to, I believe that was number 1 of looking at, is the kinetic energy conserved, or are we losing some kinetic energy? Remember, if we don't lose any kinetic energy, that means it's totally elastic. If we lose all of the kinetic energy somehow, then that's totally inelastic there, or some portion in between there. So let's go and color code this. We got a blue ball that's running due east, so this guy is going this direction at 15 meters per second. We'll call that positive. And then we got a red ball here. Oh, that's yellow. We need red ball here. Is going this way, due west. V naught, 22 meters per second. And then afterwards here, the blue ball is headed west. So afterwards here, blue ball is headed west at 21. And so then what's happening with the red ball there? Well, I could kind of do this in my head. They both have the same mass here. And so we have one that's moving slower here, faster here. And so we have a total amount of momentum here, since the mass is the same, going to the left here. So then afterwards, we must have a total momentum that's still going to the left here. Here we have a little bit, here we have 21, and for the difference here, since I'm looking at difference because they're going against each other, the difference here is just 7, and that's 7 going to the left there. So here it's got to be 7 as well, but going to the left. So then I'm guessing that red one here is going to have to be going this direction then, so that we get a difference. So we get a difference of 7 here, so that we have a total amount of 7 going to the left there. So then 7 minus that is going to be 14. So that's my guess there. But we'll go do some math and see if it is indeed moving to the right there. I don't know. We'll find out. Here's the ground that they go on. So what am I going to make my system? So I'll make my system both a blue and red ball, because then I know that the change of momentum of everything must be 0, so the momentum beforehand must be equal to the momentum afterwards. Momentum beforehand is just the momentum of blue at the beginning plus the momentum of red at the beginning, and that'll be equal to the momentum of blue at the end plus the momentum of red at the end. Great. I already know that the blue is going to be positive at the beginning and red's going to be negative there. Let's put some of this stuff in. We know that the mass is the same across all of these, so I'm just going to do m for mass, since it doesn't matter whether it's red or blue. And so then this will be the velocity of the blue one at the beginning plus the mass, and then times the velocity of the red one at the beginning. And then it'll be equal to the mass of the blue at the end plus, or times the velocity of blue at the end plus the mass times the velocity of red at the end. Hey, now check this out. If you're clever, you'll catch something right now. Wait, we could divide both sides by m and all of the masses cancel out here. That's nice. That's neat. Now let's go ahead and we can just start putting things in. We know that the blue one was going at positive 15. You can put an explicit positive there. The red one's going at negative 22. And then afterwards, we know that the blue one's going at 21, but to the left, so negative 21 plus the velocity of the red one. Hey, check that out. We can just solve for that. So I could go do that. I add the 21 over there, so I get a negative 1 overall. So then I have 14, and so then I get 14. And since we were in SI units beforehand, I know it's SI units afterwards. I get 14 meters per second. Oh, it's 14 meters per second. Okay, cool. Great. That was it. Well, not too bad. It makes it a lot easier when the masses are all the same, so they can just drop out like that. Okay, so we got the final velocity of the red ball. That's nice. Is this elastic or inelastic collision? Explained. So let's look at the change in kinetic energy. So we'll look at the energy here. Maybe I'll label this energy. And really, it's kinetic energy. So we're looking at the change in kinetic energy. Is there a change in kinetic energy or not? And that's what we're looking at. So then we'll see that it's the ending bit minus the beginning bit to see if there is a change in kinetic energy. And so let's do each one. Well, the kinetic energy afterwards is the kinetic energy of the red ball plus the kinetic energy of the blue ball. And then beforehand, it's the kinetic energy of the red one beforehand plus the kinetic energy of the blue one beforehand. And we're looking at the difference there, so there's the subtraction. So let's go do this. We have 1/2 mvr squared. Now check this out. Each one of these is going to have a mass in there, but the masses won't matter, or I could just factor all of them. I'll just leave them in. Okay. The masses won't matter. Okay, so I'm going to go ahead and I'm going to factor out the mass in all of these things here. So I'm going to put m out here. Well, no, they're all going to have a 1/2 there as well. So I'm going to put the half out there as well. Okay, so now here's the kinetic energy of the red one. I got the 1/2 m there, so it's going to be Vr plus my Vb. So that's this bit right here, and then minus. I'll put that in parentheses so it's be nice and consistent there. And then this is going to be. I'm gonna distribute, since I know that that is going to go to all of this. I'm going to have it like, be applied to all of it. So then this guy will just be the velocity of the red one at the beginning. Oh, don't forget the squares on that. Wow. Plus the velocity of the blue one at the beginning squared. Okay. So now we just got to go and we got to calculate that. Did it actually give us the mass? No, it just said they're all the same. Okay. Well, if the kinetic energy is conserved here, then we know that if I have some sort of difference inside my greater bracket here, we know that we have a change in kinetic energy. It doesn't matter what the mass will be. Some non-zero mass, it has to be a non-zero mass because they're real balls, will multiply to be some number if there's a difference in here. So let's go see if there's a difference in there. Well, let's go do that. Let's put in some numbers here. We have the VR at the end. Oh, now I got to remember all these. 14 and 21, that's right. Okay, so this will be 14 squared plus 21 squared. And then this guy was it red one's 22? Oh, I'm going to mix them up. Red one's 22 and blue one's 15. 22 squared plus 15 and then square. So now when I look at that and I go, hey, 14 squared plus 21 squared, is that equal to 22 squared plus 15 squared? I think not. But let's go grab a calculator and double check that. Yeah, so I get a difference of 70. Oh gosh, wow. I get a difference of negative 72, meaning, so I have my m over 2, and then times a difference of negative 72 is going to be equal to my change in kinetic energy. So that means that my kinetic energy is decreasing by some amount. We don't know the amount because we don't know the mass there, but it is decreasing. So is this totally elastic? Well, it's definitely not totally elastic. Did all of the kinetic energy go away, to go into something else, go into other types of energy? Well, no, not all of it, because if all of it went into other types of energies, these guys wouldn't be moving. And so it's not totally elastic, nor is it totally, oh gosh, let me write that a little bit neater. Is it totally inelastic? But somewhere in between. And we're going to leave it like that for this course there, but it is somewhere in between. Okay, cool. That's that. Have a wonderful day. See you.